Thank you very much. So I'm really happy to see a larger crowd showing up to this first EBINET lecture series. I will be talking about climate change mostly, and implications of climate change on water resources. And that almost automatically makes a link to energy systems. And I try to transport this a little bit into this talk, I hope. So terming a sensitive interface, I think this is clearly the case because it's a bilateral issue. So climate change has impacts on energy systems who, again, have large impacts on climate, its variability and change ultimately. So before I start, I realized I just had a short connection with Julia before we started, and realizing that there's a number of people in this talk who have not been exposed to EBINET yet. I'm going to make this a very, very short introduction, but just so you know what we do and what we stand for. You can always find this on our website as well, but maybe just a few words. We are actually a grassroots, bottom-up initiative, I would say. We've been around this is actually our 10th year, which is crazy. But we started out in 2011, just realizing that we had lots of things to share, and in terms of looking at the perspective of energy system transitions from an environmental perspective, from an engineering perspective, from an economic or socioeconomic perspective, and ultimately then also from computing science perspectives, would be really instrumental to maybe push the research front a little bit further into understanding how these systems interact and how these systems work. So we have, I don't know if we have developed that term, but the E-cubed systems, environment, engineering, and socioeconomics, we want to have a joint perspective to try and solve issues that are currently in the way of an effective and sustainable energy system transition. And so what we do, we run small to hopefully at some point large-scale research projects, very international, very interdisciplinary. We train highly qualified personnel. And understand this is a very important term in Canada. For us, it's also, of course, important junior researchers, young academics who will be much more relevant and much more important for the long-term goals of EBINET. And we also do regular summer schools, normally at least. We couldn't do one last year for obvious reasons. We cannot do one this year for obvious reasons. This is very, very unfortunate. But that's one of the reasons why we decided that we should at least initiate another form of communication, in this case, starting these EBINET lectures, because we also need, and that's the main reason actually for that. We've been hanging out as a group for some time, and the group has grown, which is really nice. And we've discussed together on research topics, but we hardly ever really introduced our own research, right? So what do we specialize in, and what can we potentially contribute to the whole group? And this is, this is why we have this lecture series. The key research topics, you will realize that this is a really broad spectrum of different topics that EBINET is looking into or looking at. Cleaner energy production, transportation, storage, impact of energy development on ecosystem processes, the effects of changing environmental conditions on energy systems, advanced digital technologies and energy systems research, societal, economic, and governance implications, and also interdisciplinary research designs, which is actually a quite exciting topic to work on. And we find within EBINET that this is actually really complicated, right, to get this off the ground for various reasons. We can certainly discuss this later on. Computing science was brought up a couple of times. Computer science or data science is a very key component, a very important key component to what EBINET does. And it's kind of the glue that puts everything together and that tries to bring us to another level. And I think this is really one of the core ideas that we're holding on to. And at least today, I can, from my perspective, research perspective, I can also talk a little bit about high performance computing and big data in this context. So new approaches to data analysis and artificial intelligence, including computer vision, machine learning, new strategies of data acquisition, lots of stuff being done in remote sensing technologies, where some bridges have been built between units both in Alberta and in Bavaria. And then ultimately integrated modeling and evaluation systems that are designed for this E-cubed systems approach that I just mentioned briefly before. And so we come up with this small sketch. It's supposed to illustrate on how we see the connectivity. We appreciate that none of what we do in order to obtain a more functional, more effective, more sustainable energy system in the future requires the expertise of very different disciplines. So we have to understand on how to first collaborate together and then try to put our methods together to make something that is better than just the sum of its parts. And so my perspective is the environment perspective, or ecosystem perspective, and this is what I'm trying to talk about today. So I'm back to the first slide, actually. So climate change, that's the topic, and energy systems and how that connects. I'm sure that all of you, no matter how deeply you are rooted in climate change studies, are familiar with the current rates of expectations that we have and how these systems are interconnected. Putting this in some pictures, this is actually one of the pictures I personally took in Fort McMurray in 2011, and that is quite an eye-opener to realize something about emissions. Makes the numbers quite visible in some sense. And so we're looking into different energy systems to compare with, and we're not supposed to point fingers from a German perspective on the Albertans, because the upper left picture that you see here, that is in Germany. So it's an open pit coal mine. This is from Fort McMurray. We do have, of course, the issue on nuclear power plants and some challenges that come along with that, because as our Canadian friends also might know, next year, 2022, we're actually getting off our nuclear power plants off the grid, and that still has some challenges, of course. And then on the other side, there's the renewables that are certainly needed to try and reach the goal of a smooth energy transition that is protecting climate or supporting climate mitigation targets. But at the same time, it also brings a number of to be taken into consideration when we talk about environmental impacts of energy systems. I realize that there's a number of people writing in the chat, but do you still hear me, or did we lose connection? Can anybody say something?
It's Pierre, a little confused. Yeah. Everything's good.
All right, okay. So if there's anything, you just feel free to interrupt me at any time, no problem. But I don't see any of those small tiles or faces, so I'll just keep talking unless somebody interrupts me. Okay. So how is this connected to climate change, the energy thing? And I'm sure that most of you, or all of you maybe, are aware of this report that came out from the IPCC in October 2018, talking about the global warming of 1.5 degrees and what is needed in order to reach that target. And some of you might also be aware of the figures that are typically being seen here. And what you see in yellow and orange, this is the current trajectory that we're on. And despite the severe circumstances that we had in 2020, this line is still, increasing and not stopping any pace yet, right? So this is about the concentration that we find in the atmosphere. And if we want to stabilize at something that is close to that, 1.5 degrees that we can see here in the background, there's a pointer here, that we can see here in the background, we would need to do something like this, right? So this is the net global CO2 emission pathway, and we're here, 2020, and what we would need to do in order to reach that 1.5 degrees is this, right? And the targets that have been set are quite ambitious, and sometimes, and it's certainly something that we can discuss, I have little hope that this is by any means possible. Maybe it's not even reasonable, and maybe it's not even something that could or can be done, but it's just to provide the perspective at where we are right now. And if we look at the long-term record that we have available now, the level of CO2 in the atmosphere keeps rising almost steadily. We have considerable amount of reduced emissions this year, obviously 2.4 billion tons. But at the same time, no, it's gigatons. At the same time, we can detect that the concentration of carbon dioxide in the atmosphere is still on its rise, reached more than 420 parts per million, which is substantial as compared to, let's say, just 40, 50 years ago. So in terms of a systems thinking, and that's also something I would like to talk about today in large parts, is this connectivity. My main field of research is climate variability and climate change, and how that connects to water. And then we can try to make that link to the energy system as well. So this is how I'm trying to frame this for today. And well, let's go. We have a couple of connections that we look at in this branch of EBINET. So the connectivity between energy systems and environmental impacts has many facets, many faces that need to be taken into consideration. On the one side, we have the mitigative part. So how do energy systems emit greenhouse gas into the atmosphere? But we also have the other issues on what renewables are doing to the environment and how that needs to be taken into consideration as well. So if we look at hydropower, we could fill several semesters of talks about the implications of hydropower, but aerial demand and ecosystem change is certainly something to be considered. Then, well, wind and wind turbines, they, of course, support habitat fragmentation to a large degree. Then we can also have the issue that are connected to biomass and biomass energy, where we see land degrading due to erosion in the so-called bad biomass plants, and eutrophication that we find in the water body. So water quality deterioration is also a severe problem. And then we have the hydrometeorological extremes that are really a little more at the core of my own research. And this is what I would like to talk about. An interesting framing that has, I think, created lots of momentum, especially in Germany, but probably all over Europe and maybe also in other places, is the very special situation that we had in 2018. And 2018, the whole year has been exceptionally dry, in Germany at least. We've seen times of very low wind speeds, statistically significantly lower than the usual or longer-term mean. We see that was compensated to some extent by solar power, which was more than the usual. So you can see to the left here, the wind anomalies in July that were really, really low, minus 20%. At the same time, with about 10% more solar power that we were able to use. But at the same time, and this is something where the water part comes into play, the water-cooled plants, the thermal plants that need water for cooling, they had severe difficulties in that year because the water levels in the rivers were so low that we were no longer able to extract water for cooling purposes. So they needed to shut down thermal power plants, some nuclear power plants in France, for instance, and many other issues that we found. Then we see the 2018 heat wave had a large impact on energy demand, especially for cooling. So the highest ever demand in summer was recorded in Poland as a consequence of a high demand for air conditioning. Right? So this is something that we have not seen to this extent before, but it's somehow, because what we expect for Europe to happen is that summers like the one we had in 2018 are more likely to become not a new normal necessarily, but something that is really upfront that we are facing in the coming decades. Same thing, implications, water, the low water levels that we had in the Rhine kept coal from being transported to its thermal power plant, so that was interrupted to some extent. There was cooling water problems in Karlsruhe where a 505 megawatt power plant had to be shut down for some time. And at the same time, due to the lack of water, there was also less production in hydropower. So we see that this is a very peculiar year, very special. it had impacts on all levels, basically. So the conventional, the nuclear, and the renewable energy component. And this is something that requires more considerate observation and understanding in research. So what I'm presenting, and this is nice that Benedict Kern is here, because I'm not connected directly to Concordia, but at least we speak with a lot of people in Montreal in our joint research. There's a long tradition of doing research together in climate science and climate impact studies with colleagues from Uranos, from the ETS, from the INRS, and the Centre d'Expertise Fric du Québec. And we've been running a project that deals with climate change and climate variability on hydrological extreme events. And I'm trying to present a little bit on what we do here, because this has been something we've been working on for the past few years, and we will extend this work into the next few years. And I find this, at least indirectly, highly relevant to the goals of EBINET. So I'm trying to make a connection to the energy systems part as well. So the inspiration for having this this project was triggered by the observation that very large-scale flood events kind of became more common in the past few decades. So if we look in Quebec and if we look in Bavaria, you see that over the past 20 years, we find locations in these regions where flood events happen that each qualify for a 1 in 100 year flood event or more. So that means an extreme flood, and we see 5 on the Bavarian side in 20 years, each qualifying for a 1 in 100 year flood. So that means there's something wrong in this system consideration. So when we can't really say yet what that is. Is it climate change? Maybe in parts. Is it a complete misunderstanding of what a 1 in 100 year flood event is? Could also be the case. And most likely it's something in between. But with the perspective that as a follow-up to climate change and global warming, we must expect that the intensity and frequency of downpours and very heavy precipitation is increasing, gives us some reason of concern and some reason to believe that it's worth trying to investigate whether we can find something that brings us closer to an understanding of how the mechanisms and the dynamics of these extreme events are changing. So the objectives in this research is, does climate change contribute to high intensities and frequencies of extreme events? And if yes, how? And how can we, and that's maybe scientifically the most challenging task. So how can we distinguish between natural variability of the climate system and a clear climate change signal? So I think in order to be relevant for policymakers, you have to try and be clear on what is the signal that you investigate. So how far can you go and claim that this is current climate, normal deviations, and when does climate change really start? I think only then you are in a position where you can really provide advice and governance that helps policymakers to take the right decisions. And then we were looking at the impacts on the water and energy resources that we could expect under the assumption of a very high greenhouse gas emission scenario. So for those of you who are not familiar with this term, the representative concentration pathway 8.5 is what lies underneath the assumptions that we claim throughout this whole study. And that means that until the end of the 21st century, it is assumed that anthropogenic activity will increase radiative forcing in the atmosphere by 8.5 watts per square meter. So this is really an assumption of a business as usual trajectory that really keeps CO2 emissions rising and CO2 concentration in the atmosphere rising. Just bear that in mind, because the findings are quite dramatic, and that needs to be taken into perspective. So the case studies in which we work, you see there's one European case study, there's one Eastern North American case study in our collaboration with our colleagues in Quebec. We have centered our case studies over the city of Munich and over the city of Montreal. And so what you see here is a domain of a climate model or regional climate model that we are analyzing. And as I'm focusing only on the Bavarian part, and later when we talk about water resources, here on that Bavarian small section here, I will skip the Quebec part for this talk, and at any time, if somebody's interested, we can of course come back to this if you want. Unfortunately, the domain of climate modeling does not extend far enough to the west so that we could look at Alberta as well, but maybe that could be our next experiment, right? So what we are doing, and this is kind of the workflow that is quite characteristic for what my group of environmental modeling at the department does. So we have to deal lots with uncertainty. We also deal with complexity science issues to some extent. And what was really special about this particular project is that we tried something very new. So these terms here, it's the representative concentration pathway. So that's the emission scenario. It's not in our control. Then there was a global climate model or general circulation model. You can choose what GCM stands for, but it is a global climate model. And there were 50 instances of this global climate model that we downscaled to a regional context. So a global model, typically, of course, it spans across the globe, but it has a very poor spatial resolution, very difficult to draw any specific hydrological conclusions that would be useful for a policymaker or water resources manager. So we had to downscale this from the global scale to a regional scale. So the one case study frame that you just saw. And this is something we did on Unix or Garching's supercomputer called SuperMUC. It's, I think, Klaus, Matthias, you maybe have the exact numbers, but I think it's still one of the top 20 computers these days in terms of performance worldwide. So it's a really, really big machine. And then from the climate model, we have to do some bias adjustment to downscale the information to run a more assessment. And so this is a very general way of conduct in climate impact science. But what is special about this particular one is that we did this analysis 50 times. And in 50 model members, it's a so-called single model initial condition large ensemble. That means that we have 50 climate model runs that have a very beginning of one. And since a model is a fully spaced chaotic system that is actually able to describe climate, we have 50 instances of possible climates from 1950 to 2100. And that gives us 7,500 model years that we can analyze and try and look for extreme events. And we can try and analyze to look for shifting mean levels, for shifting variabilities and standard deviations. So that just provides a very, very robust statistical database, a very robust database for statistical analysis. And so there's a number of things that we can do that were really costly in terms of computing time and computing power. So this is why this is a real high performance computing, or so it's a really big data project, big data more in a sense of data volume. So we had roughly 100 million CPU hours to use on that supercomputer. We created 500 terabytes of data times 2 for the backup that is needed. We're using the data science storage that's provided by the SuperMUC. And in terms of energy consumption, and sometimes you may have heard that climate scientists are among the worst greenhouse gas emitters, and that's unfortunately true to some extent. The computation alone took about 1 year on SuperMUC, and that required about 1.25 gigawatt hours of electricity just to run that simulation. So that is somewhat embarrassing. I think it's the equivalent to roughly 300 households' energy consumption for 1 year. But then at the end of the day, you know, we need to understand the systems better. Yes. So this is the figure that comes now is very, very stressful. And so I'll give you a few seconds to digest. So what you see here, it's our way of trying to describe what natural climate variability is. And I was mentioning that we've been working on 50 so-called members of a climate model. And on each of these tiles, you see the precipitation pattern for the coming 20 years compared to the precipitation pattern of the last 20 years. And that is not really anything that deals with climate change. This is more the variability that we're looking at. And if you just look into certain tiles, like let's say tile number 4 and tile number 6, you see they almost contradict completely, right? And you see there's lots of chaos in these pictures, and they reveal the nature of natural climate variability. So there's no climate change included here. It's just the bandwidth of what climate could look like over a given region over a given time. So why again have we been doing this? Why those 50 members? Each climate simulation is an instance of a possible climate. So we could say it could have been like this as well. So if we look out the window, you see weather. And right now it snows here a little bit, I think around 0 degrees. It could as well be -5 or +5. It could rain, could be sunshine. Well, no sunshine at this time of the day, but you know what I mean. So, and if we put this over the long term, these are instances of climate that could have happened just as much as the one that we actually recorded. Right? So we're using the advantage of using such a model as a measure for the natural variability of the climate system. And then, as I said, we are focused mostly on looking at extreme events, and extreme events are very rare by nature, obviously. And so if we 50-fy, I don't even know if that's a word, but let's say 50 times the database as compared to a normal climate, that means that if we analyze a 30-year time slice, we're not actually only having 30 years, but we're having 1,500 model years to investigate what happened in this time, in this reference time period. And we believe that this provides a statistically robust analysis and comparison of impacts that can be connected to natural climate variability or connected to actual climate change. Okay, of course, we can also aggregate the information from the 50 members, and we can look very much as to what the climate is developing overall in terms of mean values. So what you see here to the left, it's sorted by months in IPCC seasons. So that means December, January, February, March, April, May, and so forth. And we see the temperature change of the end of the 21st century as compared to the beginning of the 21st century. And you see the color bar is not very well selected, but you can see that it's getting warmer in each month, but particularly in the summer. And now if we look at the same thing, but not temperature, but precipitation, then you see here the turquoise colors mean wetting and the brownish colors mean drying. That we can clearly see that over the winter, so let's say from November through March, we see an increase in precipitation over Central Europe. And then from June to September, we see a strong decrease of precipitation. And accordingly, we can expect a strong increase in the risk of drought. Let's have a closer look at precipitation, just a few examples. Just for Central Europe, these are the very rough borders of Germany that you can see here. So for the winter, we see an increase in precipitation, in the spring also, but just slightly. And then in the summer, a very strong decline. And in the fall, also a very strong, or not as strong, but quite strong decline. So we have a very strong seasonal shift. You could also put that in months. So from January, where we have strong increases of precipitation, into July, where we have severe decreases of precipitation by -40%. That is really enormous, and that will have large consequences. So we can say winters will be much wetter, summers will be much drier. That is not so much an issue for the places that are currently dry in winter and wet in summer. But in Bavaria, we have, even though it's small as compared to Alberta, Bavaria is really small, just around 70,000 square kilometers. We have a very distinct line in its middle, and in north of it, we have a distribution of rainfall that is already winter prone, and south of it, we have a distribution of rainfall that is summer prone. So that means in areas that where we already experience winter floods, they will be more likely, and areas where we have summer droughts, they will be more severe. So that is something that we can already draw as one conclusion from this. for the sake of time, I'm going to jump over this one. This is a very complicated one. Just looking at extreme precipitation, just maybe for your records, rainfall intensities will increase according to this investigation. And we can even try and say when this increase is actually really driven by climate change, right? So we can say that in most parts of Central Europe, extreme precipitation is already now a product, or the changes in extreme precipitation are already now a product of climate change and no longer explainable by climate variability. We've also been looking into weather patterns, and there's certain weather patterns across Europe that are really very important for the likelihood of producing flood events. One of those is the so-called 5B cyclone. And the 5B cyclone, I'm not going to go into detail, but it's a rather regional development. It's a low pressure system that develops over the Mediterranean, then crosses or goes eastward around the Alpine ridges, and then comes back from the north and is being blocked on the northern side of the Alps, producing very large amounts of rainfall over consecutive days. These are called 5B cyclones. And what we've been doing, we've been trying to train the machine learning based model that investigates how these patterns are changing over time in our data set. So will those 5B cyclones become more frequent? And not really. They're not really becoming more frequent, but we can say that in all seasons, what we see that the percentage of extreme precipitation events are increasing. So the number of 5B cyclones more or less stays the same, but the ones that produce high levels of rainfall are increasing. And we can also see if there's a seasonal shift, and the seasonal shift is very obvious. So I'm sorry, I did not explain. The green box plot here represents our reference period. The blue is the near future and the yellow is the far future. So we can clearly see that there's a strong change here, that 5B cyclones will become less frequent in the summer and they move into spring. And in spring, that could eventually be a problem when it overlaps with snowmelt. So if we have a snowmelt event that is even triggered by a 5B cyclone, then we can find the flood conditions that will exceed anything that we have witnessed so far in our country. We've also been looking in heat-related things, and I'm just going to show one example. I believe that probably all of you, at least the ones the ones who are old enough, I would say, that some of you might remember the heat wave in France in 2003. Well, 2003 has been remarkably hot all over Europe, but in France it was a particularly serious heat wave. And so we tried to look into our data set to see what can we learn from that heat wave in 2003 that was a turning point in understanding the severity of heat as whatever literature source you use caused 35,000 to 60,000 fatalities in France alone. So that is really something that even stands in Corona times as a very high number. So how can we approximate what could eventually happen under a worst case scenario for Munich? And so first of all, we needed to learn what the heat wave in Paris looked like actually. And so we figured out that there's a heat wave day can be characterized when the maximum temperature per day is above 33.5 degrees Celsius, and if the minimum temperature at night is still above 19 degrees. And that heat wave was a period of 11 consecutive days that had those two criteria. So what we did, we've been screening through the whole data set that we have created in Climex in that project, and we're looking for exactly those type of events. And we found a lot of them, especially by the end of the century. So if we apply this mechanism to the end of the century to Munich, then each line is one of those climate models, one of the 50 climate models that we've used. And we see that there's some crazy heat waves coming up. So there can be heat waves. This is the worst one, right? But there are many that are much worse than anything that we have seen in 2003. Just imagine I'm not saying that this is going to be a reality. I'm saying this is under a under a possible scenario of future climates. This is something that could eventually happen. And just imagine 48 consecutive days of daily maximum temperatures above 33.5 and daily minimum temperatures above 19, so tropical nights. That is something that is going to drive our health system knock it into pieces, right? So having the knowledge of heat waves becoming more intense is something that people that work in that field should be taking care of and try to prepare as much as possible. In easier, purely statistical terms, one could claim that the risk of a 2003 heat wave increases to 68% until the end of the 21st century. That means in 2 out of 3 years, we could eventually witness a heat wave in Munich that is as severe as the one that we know from 2003. Okay, as always, I know that I need to speed up a little bit. So maybe I'm just going to concentrate on a couple of findings, the ones that are maybe more relevant for energy systems, because I haven't touched that yet. So the changes in mean runoff. These are 98 gauges in Bavaria. So river basins for which we have done this analysis. We compare the future, the end of the century, against our reference period from 1981 to 2010. And the line at 0 means that's the mean flow from the reference period. And you see in those scatter plots, in those box plots, that for almost all the gauging stations that we have modeled, simulated, we find that there's a substantial decrease in mean runoff. And you can already see what this leads to when we think about hydropower production. There's only a few exceptions, and these exceptions can be seen here. This is in the mountainous part, so in the alpine part of the hydrological Bavaria, where we see even increases, and that's due to glacier melt, right? So the glaciers that we see in the Alps are melting at very high pace, and at least as long as they are there, they can create higher mean flows than we currently have. We can also put this on a map. And this is the shape of hydrological Bavaria. We like to use this term because the hydrological Bavaria is actually quite larger than the real Bavaria, because it contains all the inflows as well. But you can see that all the reddish colors and the orange colors means there's a reduction of mean flow, and only those blue ones where you can see an increase in mean flow. And these are strongly glaciarized catchments, as I just tried to explain. We've also been, I'm jumping over this one, we've also been looking into extreme floods. So trying to look ahead. For those gauges here, we picked one. This is the, oh, that has moved. That is placed wrong. So yeah, I had to prepare the slides a little bit. This circle should actually be here, right? So, but I hope it doesn't make a difference for you. So what we see here at the Sill, which is a river that is close to Innsbruck in Austria, that's a QQ plot. So that means these are the runoff values for the reference period. These are the runoff values for the future period. This is the one-to-one line where nothing would change. And since we know that all the return periods that we have been looking at are moving to that side, means that the intensity of extreme floods are increasing. You could put this in words of return periods, meaning that what is currently a 1 in a 100-year flood will become a 1 in a 10-year flood. Right? So this is how to read this, this figure. So you could put this in two different terms. Currently, a 1 in a 100-year flood represents 250 cubic meters per second. At the end of the century, this value changes to 390 cubic meters per second. Or you invert this and say what's currently a 100-year flood will be a 10-year flood. Okay, so this is just how we try to analyze the system and see where we're heading in times of climate change. We see that for all gauges, almost all, there's a few, the pale ones here, the light, very light, more beige or brownish ones, where we see no change in the intensity of 100-year flood events. But when it comes to blue and more blue, the more blue, the stronger the intensity is. So just bear in mind that while we have less mean flow, still the intensity of heavy rainfall leads, for instance, to such flood events that are stronger than the ones we currently know. So this is quite a large challenge for water resources managers to take into consideration. What really, what is a bit frightening, I have to say, is looking into compound events. So that means if a flood event is not only triggered by one source, that is heavy rainfall, but if it comes along with something else, so like heavy rainfall on an already melting snow cover, or if we have fully saturated soils and then it rains very hard, right? So this is something that could potentially create flood events that are far above anything that we have ever recorded. And this is what we try to do. This is one catchment. This is the Rot. It doesn't make, it's not so relevant here, but the Rot catchment, and the gauging station is called Rusdorf. And what we did, so this movie is running a couple of times. This is the location. This is the location of the catchment, right? In the southeastern part of the hydrological Bavaria. You see how the soil water content increases. You see how the cumulative sum of precipitation is rising in the event that we're looking at. And what you see in this upper figure here is 295 cubic meters per second was the highest runoff ever recorded in about 80 years of observations at this gauge. And in our data set, at some point in 2060, in one of those members, we find that there's an incidence that is really way above anything ever seen. So first, we have a very strong rainfall impact that creates a flood that exceeds the current maximum. And then, very unluckily, just after this very severe short impact event, there comes a 5B cyclone. And the 5B cyclone is now producing lots of rain that falls on completely saturated soils and creates a flood with about 1,450 cubic meters per second, as compared to 295 that we had ever seen so far. So you have to consider that this is, of course, statistically seen an extremely rare event, but it gives us the means to understand of what is potentially possible. And it is absolutely impossible to protect against a flood like this. It only helps you to prepare your risk awareness plans or your preparedness plans to see how you could counteract and do civil security in terms of lacking the word just now, take people out of the danger risk zone, right? Evacuate. So yeah, evacuate. And just to put that also in another perspective, so just to give you an idea, this picture is fairly known, at least in Bavaria. So this is the flood event of 2013 that we had seen. One of the largest events ever recorded, 2,100 cubic meters per second at the Danube River. And looking at our scenarios, the one example that I just showed would create a runoff that exceeds 13,000 cubic meters per second. So more than 3,000 cubic meters per second more as compared to this event. And again, statistically very rare, but it's possible, and that is something to be taken into consideration. Looking, and just a few slides on energy, of course, we've also been trying to understand what kind of impacts that might have on energy systems. And there's several things to consider. Of course, on the one side, it's about energy supply and energy demand. And the energy demand side is somewhat easier for us to project. So what we have been doing, we were looking at heating and cooling degree days in Bavaria until the end of the 21st century. It's a very simple concept, the heating and cooling degree days. It kind of sets a threshold, and you sum up the values above that threshold, and then you have a measure for the cooling demand if you're above that threshold, and if you're below that threshold, you have a measure for the heating demand. And what we can see for the heating degree days, we can see that we need to heat much less in the future because it gets much warmer, right? So according to that, we can see where the highlighted values are, but we are in the range of the difference is quite substantial here. looking into these values. And then at the same time, when it comes to cooling degree days, we see that it is also all in plus. So we will have to invest more energy into cooling. And you see that the patterns look quite different, but especially the numbers are much different. Right? So the change is remarkably different. We will save lots of energy because we need to heat way less than we need to invest more into cooling. But first of all, the difference is the season. And second is the current energy system in place. For heating, we use to a large degree fossil fuel still. And for cooling, we use electricity to a large degree. And that is also going to have an impact on the grid. We've been looking into the hydropower implications. I know that these powerhouses, 124 megawatts, is really, really small for Canadian context, especially for the Quebec context, but it's large on the Bavarian scale. And what we've been trying to do, we've been looking into how climate change might affect hydropower generation in Bavaria under the scenario that we've been using. So what we have been doing, and this might also take a little time to analyze. So the hydropower potential at this powerhouse, and again, the gray box plots, they represent the reference period, and then blue, green, and red, they represent the future periods as we propagate into the future. And we see basically two different things. That we see, first of all, in the spring, like in March, April, and May, we see that future climate will allow us to produce more electricity due to the then available water surplus. But we also see that for a large part from July until December, the future energy production from that hydropower house will be much less. So overall, relative change as compared to today will be roughly 19% less hydropower production from that powerhouse as a result of climate change alone. So just one last example. So if I summarize the findings from this project, a few things that I would like to highlight. Please bear in mind that we have been using data from a quite sensitive climate model. And we've also been using an extreme climate change scenario, so the RCP 8.5. But what we see is quite easily connectable to water resources management and energy resources management. We see that there's a very strong increase in temperature, especially in the summer. This will increase the risk for heat waves. It will strongly increase the cooling demand, but we have an even stronger decline of heating demand in the winter season. We see a strong increase in winter precipitation, so a very strong increased risk of floods, especially in northern Bavaria. So it concerns the people at FAU more than the people at LMU and TUM. We have a strong decrease in summer precipitation, so a higher risk for drought, a strong impact on biomass production for sure. Again, unfortunately, this is something that will most likely strike northern Bavaria more severely than southern Bavaria. We have a reduction in mean annual flow. At the same time, however, a strong increase in flood risk. So even this might sound paradox, but it's not. It is quite reasonable to assume that. But both will have an impact, a negative impact on hydropower. So for the baseload production of hydropower energy, the reduced mean flow will be crucial. And for potential shutdowns of hydropower houses, the strong increase in flood risks may also be of relevance. So we see that climate change has very strong implication for multiple domains, actually for all, especially those that work outside or in the field or over large areas like agriculture, forestry, water resources, energy resources, or the health sector. And our government, at least in Bavaria, has realized that there is a problem that might be more important than floods, and that's droughts. So the fear of running into major droughts and long-term droughts were alongside all those implications that we have seen from the 2015 drought and the 2018 drought, most of all, has now led to a CLIMEX project phase 2, where we look at droughts and low flows in particular, into land use change also, and into weather patterns. So using deep learning now, try and forecast droughts in a way. For anyone who's interested in using any of the data, it's free, so you can download the data if you want. Problem is we cannot really provide services to extract data for you, so you need to deal with large chunks of data. So if you have disk space available for a couple 100 terabytes, then just feel free and we can initiate the download process. No, seriously. So if you're interested in some of the Canadian data or some of the European data, you're more than welcome to let me know, and we would be happy to share the data with you anytime. So as a last slide, what is there to conclude from an EBINET perspective? I think we can all agree, more or less at least, that the very ambitious climate mitigation targets that Europe has even now enforced just very recently, to my surprise, to be honest, but also to my great pleasure. It requires a rapid and effective transition of energy systems. And what we see, however, and that is something that always puzzles me, and maybe I'm not talking to the right people, but from my horizon, I see a lot of people discussing energy transitions and moving towards renewables, but at the same time neglecting, at least to some extent, that all major renewable energy sources are directly linked to climate. And so whenever climate changes, and in some ways it changes in a not fortunate way, it will also have an impact that, from what I believe, is more than just academical, right? In running a system or moving a system more into renewables, which I'm a great fan of, it also needs to be taken into consideration that this is really connected to climate change as well. So please bear that in mind. Climate change is very likely to have substantial impact on renewable energy systems. It changes seasonal energy demand and supply. It increases vulnerability and uncertainty of the system. So especially if you have an increase in variability, there's also an increasing risk maybe of a Dunkelflaute. And I still don't know how to translate that into English, but Dunkelflaute is a term that Jürgen can explain much better than I. No wind during the winter at night. Just imagine that. And if that is for a long time, you have no solar and you have no wind, and then you have a problem, right? What I was not able to talk about, but what is quite relevant also in the context of EBINET, is that we have renewable energies that must be carefully monitored and managed to reduce and avoid environmental impact. There's many of these concerns that we have. And taking into the consideration the benefits of reducing greenhouse gas emissions also comes at a price that needs to be looked at from various perspectives, also the ecosystem perspective and the way how the energy transition affects ecosystem services as well. So this is another part of things that we are looking into in my research unit, and that we try to bring to EBINET. So ultimately, we believe, and I think this is common ground for all EBINETers, innovative interdisciplinary research is needed to better evaluate the co-evolution of energy systems and ecosystems to foster sustainable development under climate change. It is a grand opportunity for us, and if this small lecture has made you curious to learn more about this and contributes to your interest into EBINET altogether, I'd be really very happy. And with this, I'd like to thank you for your attention. And I know that I've reached the time limit a little bit, but I have to say I started late. And second, I hope you forgive me. Not too much of a problem, I hope. So thank you.